Hi, we are from Aldehyde Architects Group. We are going to present our ChemE project. As our reactant ozone, it is an harmful air pollutant that affects people and the environment. It's formed in the atmosphere through chemical reaction between pollutant emit from vehicle, industrial process, fossil fuels, and combustion. So, inhalation of the gas causes inflammation of the tissue lining human arrays. So, plants exposed to ozone are also affected as productivity is impacted due to damaged plant cell and tissues. Okay, let's move on to synthesis route. So, we are introduce ozone analysis of alkene. So basically, ozone analysis is a process involving oxidation process of alkene with ozone which act as oxidizing agent that can produce aldehyde and more other compound. So as we can see here, the chemical structure and chemical reaction for the ozone analysis of alkenes. So in this reaction, ozone react with cis-butyene, causing oxidative cleaving, replacing C double bond C to C double bond O. So this is resulting in carbonyl product which is acetaldehyde. For the ozone analysis of alkene mechanism, the first step is ozone is added to cis-butyene, forming a fine membrane that we refer as molozonide. And then this species quiet and stable, which is cause it to break apart and forming carbonyl and carbonyl oxide molecule. And then the carbonyl molecule and the carbonyl oxide molecule generate in step 1, undergo rearrangement and forming a stable ozonide intermediate. And then this form will undergo reductive workup. The last step for the mechanism, dimethyl sulfide is used as a mild reducing agent. This is to reduce the ozonide intermediate, which are unstable and need to be reduced to form carbonyl product. It acts as a nucleophile, donating electron to the ozonide. This cleaving the structure into aldehyde product. This process breaks peroxide bond to form acetaldehyde. This step is called as reductive workup. As we can see here, this is some of the physical properties of our product, which is acetaldehyde. Acetaldehyde is also known as ethanol, ethylaldehyde, and acetaldehyde. It used for raw material for manufacturing building materials. It also used in intermediate in the production of acetic acid, disinfectant, drug, and aniline dyes. It can naturally found in the red fruit, coffee, bread, and is produced by plants as part of normal metabolism. It looks is like flammable, colorless liquid with a pungent odor, has fruity, pleasant fragrance in dilute concentration. For the reactor selection, we have decided to use the CSTR as a reactor where reactant and solvent flow into the reactor while the product of the reaction concurrently exit. So, CSTR is known for efficient mixing and stable, uniform performance under steady state conditions.
There are a few reasons why CSTR is the chosen reactor. First is uniform mixing. The continuous agitation ensures that reactants are thoroughly mixed. This maximizes the contact between reactants, ensuring efficient reaction. Next is its steady state operation. In CSTR, reactants are continuously added and products are continuously removed. The steady state operation ensures a constant flow of acetaldehyde, avoiding accumulation of products and unwanted secondary reactions. Next is its temperature control. A CSTR can be equipped with a cooling jacket to maintain a stable reaction temperature. This can be essential for ozonolysis reactions which are exothermic and require precise temperature control. This is to avoid side reactions or product degradation, such as over-oxidation of acetaldehyde. Its residence time control is also an essential point. CSTR allows precise control over residence time by adjusting flow rates and reactor volume. This is crucial for the reaction of ozonolysis that require optimal residence time to maximize the conversion of cis-butyene to acetaldehyde. How does this mini plant align with Sustainable Development Goals? For SDG 7, Affordable and Clean Energy, the production of acetaldehyde is a part of circular economy, where waste materials or byproducts are utilized. The project also indirectly supports clean energy goals by reducing ozone pollution, which may impact solar energy efficiency. Reducing the amount of ozone gas in the environment helps clean the air, thus improving the performance of solar panels. For SDG 9, Industry, Innovation and Infrastructure, the project encourages technological innovation by implementing controlled ozonolysis to minimize environmental harm and improve industrial efficiency. This mini plant can serve as a prototype for sustainable chemical processing infrastructure. For SDG 12, Responsible Consumption and Production, the reactor is designed to maximize reactant conversion, reducing waste of ozone and cis-butyene. The mini plant enables production of acetaldehyde in small batches, which reduces overproduction. Last but not least is SDG 13, Climate Action. The reaction in the plant utilizes ozone. This minimizes harmful emissions and prevents the escape of ozone into the atmosphere, reducing the damage caused to the environment.
For the calculation part, the assumptions that we have made is 1 mole of feed, which consists of the 50% of the butene and the ozone. It is isothermal condition with temperature of 25 degrees Celsius. The pressure drops from 3 bar to 2.4 bar. The reaction is elementary, which the rate law is equals to minus RA equals to KCA CB power 2 over 3, where A is the butene, B is the ozone. The volume of the reactor is 1.65 dm cube. Volumetric flow rate is 0.2 dm cube per minute. From this calculation, we know that the butene is the limiting reactant. This is the stoichiometric table. Since all the species is in the gas phase, so we use the formula on top of the table to get the formula of the concentration. Based on the equation, YA0 equals to YB0 equals to 0.5. Delta is 1 over 3, and times with the YA0 to find the value of the epsilon. The volume of the reactor is calculated by using the formula of the cylinder, which is pi r square h. Activation energy and the pre-exponential factor is given, so we can use the Arrhenius equation to find the value of K. The formula of the concentration is substituted inside the rate law equation. After that, the rate law equation will be substituted inside the CSTR design equation to form a new equation. When different values of the CNO is substituted inside this equation, we will get a different value of the conversion. The U is calculated by using the formula of the rate of reaction of the desired product over the rate of reaction of the main reactant times with the conversion, so we can get the value of the 1.904. This is the MATLAB script. For the given parameters, the initial concentrations is for the manipulation and will substitute inside the conversion equation. The results of the conversion and the yields is calculated and displayed in the table. The two graphs are plotted, which is conversion versus initial butane concentration and the yield versus initial butane concentration. From this table, we know that the maximum conversion is 0.95 while the maximum yield is 1.904. For the first graph, as the initial concentration of the butane increases, the conversion initially increases, but the rate of increase gradually slows down as the concentrations approach 5.1 mole per dm cube, indicating a plateau effect. This trend suggests that the reactor efficiently converts butane at higher initial concentrations, but the gain in the conversion diminished beyond a certain point due to the reaction equilibrium and the reactor limitations. The second graph has similar trend as the conversion of the butane. The yield initially increases, but the rate of the increase gradually slows down as it approaches a yield of 1.904.
Let's walk through the process of producing acetaldehyde via the ozonolysis of cis-but2-ene. First, the process begins with two reactant storage tanks, one containing cis-but2-ene and the other ozone. The cis-but2-ene is pumped while ozone is compressed to ensure consistent flow. Both reactants are then combined through valves and introduced into the reactor. The combined reactants enter a jacketed CSTR. Continuous stirring ensures uniform mixing, maximizing contact between ozone and cis-but2-ene for efficient reaction. Cooling water circulates through the jacketed to manage the exothermic heat of the ozonolysis reaction, preventing over-oxidation of the product. In a reactor, ozone cleavates the double bonds in the cis-but2-ene, forming unstable ozonides. These intermediates need further processing to become stable products. The reaction mixture moves to a mixer where dimethyl sulfate is added. Acting as a reducing agent, it breaks down the ozonides into acetaldehyde, the desired product, while minimizing hazardous byproducts. The mixture then flows into a separation tank. Here, byproducts are removed and unreacted materials are recycled back into CSTR to improve efficiency. The purified products passes through a condenser where cooling water helps condense acetaldehyde into its liquid form. The final product, acetaldehyde, is collected for use in various industrial applications.
Moving on to the AutoCAD design of our mini reactor, all units are carefully dimensioned and arranged to meet the ChemE Cube project's 1 by 1 by 1 foot requirement. The jacketed CSTR is the largest unit with a diameter of 0.33 feet and a height of 0.67 feet. The mixer where dimethyl sulfide is introduced is a compact with a diameter of 0.17 feet and a height of 0.33 feet. The separation column, the tallest unit, is at 0.75 feet in height and 0.2 feet in diameter, which effectively isolates the acetaldehyde vapor. Finally, the condenser measuring at 0.5 feet in diameter and 0.33 feet in height ensures the cooling and liquefaction of acetaldehyde product. This arrangement optimizes space efficiency while maintaining a seamless and controlled process flow. In conclusion, the reaction is most efficient at concentration of 5.1 mole decimeter cube, achieving a conversion of 0.952 and a yield of 1.904. Higher concentrations show diminishing returns due to factors like flow rate or pressure limitations. Enhancing performance could involve increasing residence time, adjusting pressure, or safely raising the temperature to improve reaction kinetics.